now we continue with the colligative properties in the liquid solutions chapter. We so far have discussed about the concentration terms, the types of solutions, the concentration terms, vapor pressure of a solution, ideal, non-ideal solutions. Again, in the non-ideal solutions we discussed about the solutions, non-ideal solutions with positive deviation and with negative deviation, with examples and their characteristics. Now, in this topic of colligative properties, what we define, first of all, what is a colligative property, what are the different types of colligative properties, how to measure a colligative property, and what are the uses of the colligative properties is what we are going to discuss. Now, first of all, colligative property is a property of a solution, which is dependent on particle concentration of a solute in the solution. So, the meaning is, it is a property of a solution which is dependent only on particle concentration of the solute, means it is dependent on molarity or molality or mole fraction of solute in solution. That is what is the concentration means. The different concentration terms is what already we discussed. So, it depends on the concentrations of the particle concentrations of the solute, but it is independent of nature of solute. Meaning is, whether the solute is NaCl or KCl, property is same. Similarly, whether the solute is urea or sucrose, the property is same, but the property is different if it is even though solute is same but differ in concentration. That is, suppose if you take 0.01 molar NaCl and 0.005 molar NaCl, the solute is same but concentration is different. So, property changes. Now, so those properties that will change with the concentration only, not on the nature of the solute, is what we define as colligative property, right. So, now what are the different types of these colligative properties? These are the colligative properties are, so which are dependent, again I am writing dependent only on concentration of solute. What are they? One is relative lowering of vapor pressure. Second one is elevation in boiling point, EBP. Depression or decrease in freezing point, 4 osmotic pressure. The colligative properties are 4 in number. They are relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. What is vapor pressure? What is lowering of vapor pressure? What is relative lowering of vapor pressure? This already in our previous classes we discussed. Just as a immediate recollection, for I write that P naught minus Ps by P naught is equal to mole fraction of solute. P naught is the vapor pressure of the pure solvent, Ps is the vapor pressure of the solution. P naught minus Ps is decrease in vapor pressure, that is what we call it as lowering in vapor pressure. Lowering in vapor pressure divided by vapor pressure of the pure solvent, that is relative lowering of vapor pressure, is equal to mole fraction of solute. So, this relative lowering of vapor pressure is dependent only on mole fraction of solute, but it is independent on what solute it is. So, it is a colligative property. So, whether you take 0.01 molar urea or 0.01 molar sucrose or any 0.01 molar undissociated or unassociated solute over here, then the relative lowering in vapor pressure of that particular solution will be same. So, this already we have discussed. Now, I will discuss in detail about elevation in boiling point, depression in freezing point, and osmotic pressure. What is boiling point first of all? Before going to elevation in boiling point, first I should tell you what is boiling point. In fact, you people must be knowing that boiling point is nothing but the temperature at which liquid and vapor are in equilibrium, or the temperature exactly at which a liquid starts boiling. Liquid vapor equilibrium, where it exists exactly, that is what we call the boiling point. Liquid starts evaporating, liquid undergoes boiling. In fact, evaporation is again of course different from boiling, right. Now, in terms of vapor pressure, how do we relate this boiling point? Now, you can define boiling point in terms of vapor pressure as the temperature at which the vapor pressure of liquid becomes equal to atmospheric pressure. The temperature at which vapor pressure of a liquid becomes equal to atmospheric pressure. What is normally the atmospheric pressure? We take 1 atmosphere. Every liquid will have its own vapor pressure, as already we have discussed. For example, the other day in the other lecture we discussed about volatile and non-volatile liquids. Volatile liquid means which evaporates fast, whose vapor pressure is relatively high. So, if you take two liquids in which one is more volatile and one is less volatile, the more volatile liquid whose vapor pressure is more obviously will reach to a becomes equal, reach atmospheric pressure at relatively lower temperature. That is the reason that a more volatile liquid will have lesser boiling point. This in fact we can show graphically also. So, the temperature at which the vapor pressure of a liquid becomes equal to atmospheric pressure. The other way around, with an example, if I say, take the example of water at 27 degrees Celsius, water will have certain vapor pressure of about 15 mm or 13.8 mm. But as we keep on raising the temperature from 300 Kelvin to 373 Kelvin, that is 100 degrees Celsius, its vapor pressure increases to 760 mm. I will put it as vapor pressure of water at 100 degrees Celsius is equal to 1 atmosphere. Therefore, we can say that boiling point of water is equal to 100 degrees Celsius. So, the other way of defining boiling point is that temperature at which vapor pressure of liquid becomes equal to atmospheric pressure. That is the boiling point. Now, with if you add a solute into the pure solvent, for example, you add sodium chloride to water. According to Raoult's law and vapor pressure concept, already we have discussed it, and we ensured that when you add a non-volatile solute, vapor pressure of the liquid decreases. So, when the vapor pressure of the liquid decreases, now when you compare a pure liquid, this is pure solvent, and here you take a solution. Solvent vapor pressure, as we told, P naught, solution vapor pressure is Ps, and we already told that Ps is less than P naught. So, when the Ps is less than P naught, now both will have the vapors. Obviously, for a solution, the boiling point Tb dash I will call will be greater than Tb naught, where Tb naught is the boiling point of the pure solvent, Tb dash is the boiling point of the solution. So, Tb dash is greater than Tb naught. The meaning is that boiling point of the solution is greater than boiling point of the pure solvent. This difference, whatever is there, Tb dash minus Tb naught, that increase, whatever the amount of increase is taking place in that temperature, that is the boiling point, that increase in temperature is what we call elevation in boiling point. How does this elevation in boiling point relates to the concentration? Now we discuss.